In this video, we will discuss sum of z raised to n plus z bar raised to n, where z is a complex number a plus ib and z raised to n will be a plus ib raised to n, and z bar is its conjugate, which is a minus ib, and z bar raised to n will be a minus ib raised to n, and hence z raised to n plus z bar raised to n will be a plus ib raised to n plus a minus ib raised to n, and this, which we will later prove, is 2 r raised to n cos n theta, where r square is this a square plus this b square, and theta is tan inverse of b upon a. Hello friends, you are watching YouTube channel Number Collage. This channel features videos on mathematical concepts. Effort has been made to explore the concepts through basic mathematical ideas. Hope you will like my effort. We will understand this by plotting complex numbers z and z bar in an argand plane. We represent z by point P and z bar by point Q. Coordinates of point P are a comma b, and that of point Q are a comma minus b. Here z and z bar have the same moduli r, but their arguments theta and minus theta are equal in magnitude and opposite in sign. Perpendicular from P and from Q on the positive x-axis is r, such that OR is A and PR and QR each equal to B. In right triangle ORP and ORQ, by Pythagoras theorem, modulus r square will be a square plus b square, and argument theta will be tan inverse of b upon a. Here point P represents the complex number a plus ib in Cartesian form, whose polar form will be r times cos theta plus I sin theta, and point Q represents complex number a minus ib, whose polar form will be r times cos theta minus I sin theta. Now a plus ib raised to n will be r raised to n cos theta plus I sin theta whole raised to n, which according to DeMoivre's theorem will be r raised to n cos of n theta plus I sin n theta. Similarly, a minus ib raised to n will be r raised to n cos theta minus I sin theta raised to n, which by DeMoivre's theorem will be r raised to n cos n theta minus I sin n theta. Now we will add statement 1 and statement 2 to get a plus ib raised to n plus a minus ib raised to n equals r raised to n cos n theta plus r raised to n I sin n theta plus r raised to n cos n theta minus r raised to n I sin n theta. Now r raised to I sin n theta minus r raised to n I sin n theta is 0, and finally what we get is an important result: a plus ib raised to n plus a minus ib raised to n equals 2 r raised to n cos n theta. We will use this result a plus ib raised to n plus a minus ib raised to n equals 2 r raised to n cos n theta to deduce 1 plus I root 3 raised to 8 plus 1 minus I root 3 raised to 8 equals minus 2 raised to 8. If we compare this LHS with this LHS, we find a equals 1, b equals root 3. So a square plus b square will be 1 square 1 plus root 3 square 3, which is 4, but this is r square. Therefore, we get modulus r equals 2, and argument theta is tan inverse of b upon a, that is root 3 upon 1 or simply root 3. But tan inverse of root 3 is pi by 3, which is 60 degrees. Now we write the left hand side, which is this 2 r raised to n cos n theta, that is 2, r is 2, so it will be 2 raised to 8 cos of n is 8 and theta is pi by 3, so it will be 8 pi by 3. This becomes 2 raised to 9 cos of, we split 8 pi by 3 as 2 pi plus 2 pi by 3, which will be 2 raised to 9. Now this 2 pi being even integral multiple of pi by 2, cos of this allied angle will be cos of 2 pi by 3. Now this angle falls in the first quadrant, therefore cos will be positive. That will be 2 raised to 9 cos of, we split 2 pi by 3 as pi minus pi by 3, which will be 2 raised to 9. Now this pi being an even multiple of pi by 2, cos of this allied angle will be cos of pi by 3, but this angle pi minus pi by 3 falls in the second quadrant, and in the second quadrant cos is negative, so this will be minus 2 raised to 9 cos of pi by 3. This will be minus 2 raised to 9 and cos pi by 3 is 1/2, so that gives minus 2 raised to 8. Hence proved. In the next problem, we evaluate 1 plus I raised to 100 plus 1 minus I raised to 100. Comparing this with a plus ib raised to n plus a minus ib raised to n equals 2 r raised to n cos n theta, we get a equals 1, b equals 1. So a square plus b square will be 1 plus 1, 2, but this is r square. Therefore, modulus r will be root 2. Argument theta will be tan inverse of b upon a, which is 1. But tan inverse 1 is pi by 4 radians, that is 45 degrees. 1 plus I raised to 100 plus 1 minus I raised to 100 equals to r is root 2, that is 2 raised to half raised to n, but n is 100 into cos of 100 into theta. Theta is pi by 4, so it will be 100 pi by 4. This becomes 2 into 2 raised to 50 into cos 25 pi, which we write 24 pi plus pi. This will be 2 raised to 51. 24 pi is an even integral multiple of pi by 2. So cos will remain cos and it will be cos pi. So finally this value will be 2 raised to 51, and cos pi being minus 1, it will be minus 2 raised to 51. So this value will be minus 2 raised to 51. In the next problem, we have to prove that minus 1 plus I root 3 upon 2 raised to n plus minus 1 minus I root 3 upon 2 raised to n equals minus 1 if n equals 3k plus minus 1, and it is 2 if n is 3k where k is an integer. Here, since the value of n, which is a rational number, and value of k, which is an integer, is not specified, we will not use the result which we have proved directly in order to avoid the confusion with the signs. So we will prove this directly. We have minus 1 plus I root 3 by 2 equals minus half plus I root 3 by 2. For minus half, we write cos of 2 pi by 3 plus I. For root 3 by 2, we write sine of 2 pi by 3. If we raise minus 1 plus I root 3 by 2 to power n, then according to DeMoivre's theorem, this will be cos of 2n pi by 3 plus I sin 2n pi by 3. Similarly, minus 1 minus I root 3 upon 2 whole raised to n will be cos 2n pi by 3 minus I sin 2n pi by 3. This will be 2 cos 2 pi by 3 and n is 3k plus minus 1, which will be 2 cos 2 pi k plus minus 2 pi by 3. Since k is an integer, 2k will be even and therefore 2 pi k will be an even integral multiple of pi by 2. Therefore, this will be 2 cos 2 pi by 3, which is 2 cos pi minus pi by 3. This will be 2 since pi is an even integral multiple of pi by 2. This cos will remain cos of this pi by 3. And since this whole angle pi minus pi by 3 lies in the third quadrant in which cos is negative, this will be minus 2 cos pi by 3. Further, it will be minus 2 cos pi by 3 is half, which will be minus 1 as required here. Now we will substitute n equals 3k. So this will be 2 cos 2 into 3k pi by 3, which will be 2 cos 2k pi. This will be, since k is an integer, 2k is even, so 2k pi will be an even multiple of pi, and cos of even integral multiple of pi is 1, so this will be 2 as required here. In the next problem, if z is minus 1 plus I root 3, then for an integer n, we have to prove that z raised to 2n plus 2 raised to z into z raised to n plus 2 raised to 2n equals 0 if n is not a multiple of 3. We have to write this z as 2 times minus half plus I root 3 by 2, because we can write this as 2. For this minus half, we can write cos 2 pi by 3 plus I. For this root 3 by 2, we can write sin 2 pi by 3. Raising this z to integral power n, it will be 2 raised to n into raised to n, which will be 2 raised to n, and according to DeMoivre's theorem, into cos of 2n pi by 3 plus I sin 2n pi by 3. We name this 1. From this, 1 upon z will be 1 upon 2 cos 2 pi by 3 plus I sin 2 pi by 3, which will be 1 half cos 2 pi by 3 plus I sin 2 pi by 3 raised to minus 1. Raising this to power n, 1 upon z raised to n will be, by DeMoivre's theorem, cos of 2n pi by 3 minus I sin 2n pi by 3 upon 2 raised to n. We name this expression 2. Now from this expression 1, we get this z raised to n upon this 2 raised to n, which will be this whole bracket. We name this expression 3. From expression 2, we get this 2 raised to n upon this z raised to n equals this whole bracket. We name this expression 4. Next, we will add expressions 3 and 4 and write z raised to n upon 2 raised to n plus 2 raised to n upon z raised to n will be I sin 2n pi by 3 minus I sin 2n pi by 3 will be 0, and cos 2n pi by 3 plus cos 2n pi by 3 will be 2 cos 2n pi by 3. We will rewrite this step z raised to n upon 2 raised to n plus 2 raised to n upon z raised to n equals 2 cos 2n pi by 3. We have to prove z raised to 2n plus 2 raised to n into z raised to n plus 2 raised to 2n equals 0 when n is not a multiple of 3. But before that, let us see what happens to cos 2n pi by 3 when n is a multiple of 3, that is when n equals 3k, where k is an integer. Cos 2 into 3k pi by 3 will be cos 2k pi. Here 2k is even, and we know that cos of even multiple of pi is 1. Next we will check what happens when n is not a multiple of 3. When it is 3k plus 1, it will be cos of 2 pi into 3k plus 1 upon 3. It will be cos of 2 pi k plus 2 pi by 3. Again, since 2k pi is an even multiple of pi by 2, it will be cos 2 pi by 3, which we know is minus half, because this angle 120 lies in the second quadrant in which cos is negative. Secondly, when n is not a multiple of 3, we have n equals 3k plus 2, that gives cos of 2 pi into 3k plus 2 upon 3, which will be cos of 2 pi k plus 4 pi by 3, that will be cos of 4 pi by 3. This we can write cos of pi plus pi by 3, which will be cos pi by 3. And since this angle lies in the third quadrant in which cos is negative, this will be minus cos pi by 3 or minus half. We observe that when n is not a multiple of 3, this left hand side z raised to n upon 2 raised to n plus 2 raised to n upon z raised to n will be 2 multiplied by this minus half, which is minus 1. This further becomes z raised to n into z raised to n, z raised to 2n plus 2 raised to n into 2 raised to n, 2 raised to 2n upon 2 raised to n z raised to n equals minus 1. After cross multiplication, this will be, and finally it will be z raised to 2n plus this 2 raised to n z raised to n plus 2 raised to 2n equals 0, which we have to prove here. Friends, if you like this video, please click the like button. Share this video with your classmates. Don't forget to subscribe this channel. Make constructive comments to help improve my videos. See you in the next video. Until then, keep watching Number Collage. Thank you.